Pluto, a far-off and confounding divine body, was once essential to our planetary family. However, recent disturbing statements from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into public attention. They have made a frightening discovery. Pluto may be on a potential impact course with Neptune. But how could such an event occur, and what might the consequences be? Is this an uncommon cosmic anomaly, or is there more to this impending celestial impact? Join us as we explore the possibilities of a potential Pluto-Neptune collision. Pluto, once classified as a planet but later redefined as a dwarf planet due to its unusual orbit, continues to captivate the scientific community. According to recent research by leading scientists, Pluto's trajectory is dangerously close to Neptune's orbit. Prominent astrophysicists like Tyson and Kaku are raising alarms about the potential for a catastrophic collision between these two celestial bodies, a scenario that could pose a significant threat to Earth. But how could such an event happen? Unlike any other planet in our solar system, Pluto's journey around the Sun is highly unusual. It takes a remarkable 248 years to complete just one orbit. Since its discovery in 1930, Pluto has not even completed a full revolution, adding to its mystery. Pluto's orbit is not only slow but also highly elliptical, vastly different from the more circular orbits of larger planets. To complicate things further, Pluto's orbit is tilted at an angle of 17 degrees to the plane of the solar system. This inclination makes its path far more extreme than that of other planets, adding layers of complexity to its movement. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's orbit. For about 20 years of each orbit, Pluto moves closer to the Sun than Neptune, defying our usual expectations based on planetary positions. Naturally, this raises the question, why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other celestial bodies, particularly the giant planets. The study of Pluto's orbit began soon after its discovery. Early astronomers were puzzled by its unusual path. Unlike other planets, whose orbits align relatively well with the ecliptic plane, Pluto's orbit stood out due to its steep tilt and elliptical nature. The realization that Pluto's orbit crosses Neptune's was a major point of scientific interest. Despite these anomalies, the stability of Pluto's orbit is a remarkable feature of celestial mechanics. The phenomenon known as the three-body problem comes into play when studying the movements of Pluto, Neptune, and the Sun. This problem involves understanding how three celestial objects move and influence each other through gravitational forces. Predicting their paths is a complex task, and this is where concepts like AIML libration, scope libration, and VZK wobbling become important. The concept of AIML libration refers to the fact that when Pluto crosses Neptune's orbit, it remains at least 90 degrees away from Neptune, ensuring their paths do not intersect. Scope libration describes the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other massive planet, it is positioned above the plane of their orbits, providing additional protection from potential collisions. Another crucial factor is VZK wobbling, named after researchers VZ and K, who studied how space objects interact through gravitational forces. This phenomenon explains how the gravitational pulls of Pluto, Neptune, and the Sun influence each other, keeping Pluto's path stable despite its seemingly erratic behavior. Even though Pluto's orbit may appear unpredictable, this wobbling mechanism ensures its steady motion over long timescales. These intricate forces help maintain Pluto's orbit, preventing it from colliding with Neptune or veering off course. The three-body problem is essential to understanding how orbits change due to the gravitational influence of multiple objects. Studying this problem provides deeper insights into Pluto, our solar system, and even distant celestial bodies and their stars. Mathematical simulations conducted in the late 1980s revealed that, despite Pluto's stabilizing factors, its orbit remains chaotic. Small changes in its initial conditions could lead to significant variations over millions of years. However, despite this inherent chaos, Pluto's orbit remains stable over incredibly long time periods, effectively keeping any potential disruption in check. Recent computer models have provided new insights into how the gravitational forces of giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit. These models show that Pluto's relationship with Neptune is unique. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps stabilize Pluto's orbit. But Neptune is not the only force at work. Jupiter's gravity plays a crucial role, as does Saturn's, providing additional stability. These simulations demonstrate that Jupiter's gravitational influence alone is strong enough to keep Pluto in a stable orbit for billions of years. Together, Neptune, Jupiter, and Saturn work in tandem to keep Pluto safely on its course, preventing any catastrophic collisions or other disturbances. These gravitational forces are essential for maintaining order in the solar system. Without them, the system would be much more chaotic, with planets and dwarf planets like Pluto potentially colliding or being ejected from their orbits. Understanding Pluto's orbit is crucial to gaining a clearer picture of our solar system's dynamic nature. Pluto's case serves as a great example of how even the most seemingly unstable orbits can achieve stability through the intricate interplay of gravitational forces. It also highlights the importance of continuous observation and research to better understand our place in the universe. The study of Pluto and its orbit illustrates the unpredictable nature of celestial mechanics. The concept of orbital chaos, which refers to the extreme sensitivity of a body's orbit to its initial conditions, is clearly visible in Pluto's case. Even the smallest change in Pluto's position or velocity could significantly alter its orbit over time. Simulations have played a crucial role in helping researchers understand Pluto's movement. These computer models use complex mathematics to simulate how Pluto and other celestial bodies interact gravitationally. By tweaking small variables, astronomers can see how tiny changes can drastically impact Pluto's long-term orbit. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. While it may be stabilized by factors like AIML and scope libration, it can still be irregular. Even slight differences in Pluto's initial position or speed can lead to dramatic changes in its orbit over long periods. Despite the apparent disorder, Pluto's orbit remains relatively stable, enduring for billions of years. This demonstrates that, while its path may seem chaotic, there is an underlying order to it. Pluto's orbit reminds us of how much is still unknown. Understanding the gravitational interactions of giant planets with Pluto provides valuable insights into the broader dynamics of the solar system. It reveals how the positioning of each celestial body plays a crucial role in maintaining cosmic balance. Planets can have extensive impacts, affecting the strength and direction of different bodies inside the framework. So why are astrophysicists raising concerns about a potential crash between Pluto and Neptune now, after such a long time? Neil deGrasse Tyson, a leading astrophysicist and a prominent figure in promoting the study of cosmology, provides an insightful perspective. Tyson, known for advocating the renaming of Pluto as a dwarf planet, believes that this shift reflects our ever-evolving understanding of the solar system. He does not see Pluto's renaming as a downgrade, but rather as an advancement in our knowledge of the various bodies orbiting our Sun. Tyson's approach to celestial mechanics is rooted in continuous learning. He sees Pluto's eccentric orbit as an indication of how much more there is to discover in space. The fascination with questions such as the potential for catastrophic events between Pluto and Neptune continues to captivate both scientists and the general public alike. Tyson's predictions about Pluto's future take into account its highly irregular orbit, acknowledging that anything from a close flyby to a disastrous collision remains within the realm of possibility. Michio Kaku, another renowned physicist, joins the chorus of experts raising concerns about Pluto's long-term future. Kaku, known for his work in theoretical physics, delves into the mathematics behind the potential interactions between Pluto and Neptune. His theories suggest that while Pluto's orbit appears stable today, its future remains uncertain. He warns that, over time, even minor changes in the gravitational forces between Pluto, Neptune, and other planets could lead to a catastrophic event. Kaku's predictions highlight the vulnerability of Pluto's orbit despite its current stability. As we continue to explore cosmic mechanics, it is essential to consider Pluto's orbital fate. Although current models suggest that a collision with Neptune is unlikely in the near future, the unpredictable nature of celestial dynamics means we can never fully rule out such a possibility. Gravitational interactions with other celestial bodies will continue to shape Pluto's trajectory, and even the gradual transformation of the Sun into a red giant, eventually collapsing into a white dwarf, could alter the gravitational landscape of the solar system, potentially affecting Pluto's orbit. While the likelihood of Pluto colliding with Neptune anytime soon seems remote, the inherent uncertainty in predicting celestial mechanics over such vast timescales means that anything is possible. The forces at play in orbital mechanics are powerful and complex, and even the smallest change can accumulate over billions of years, potentially leading to significant shifts in the orbits of distant objects. This uncertainty in space exploration brings us back to a core principle. The more we learn about the universe, the more we realize how much remains unknown. The study of Pluto and other distant objects in our solar system continues to challenge our understanding of planetary orbits, gravitational interactions, and the fundamental laws that govern the universe. As scientists continue to observe Pluto and Neptune, new data may either reinforce or challenge our current theories. While the idea of a catastrophic encounter between Pluto and Neptune may seem far-fetched, it serves as a reminder of the mysteries that space still holds. As our tools for space exploration advance, providing us with more precise ways to simulate, predict, and observe these cosmic phenomena, the possibility of a collision, or even a close encounter, between Pluto and Neptune remains a compelling example of the complexity and unpredictability of our solar system. Whether such an event will ever occur is unknown, but it highlights the ever-changing nature of our cosmic environment. The story of Pluto's orbit invites us to think beyond what we currently know and to embrace the mystery of space. It challenges us to look at the universe with fresh perspectives and to remain open to the surprises that lie ahead. As scientists continue to unravel the secrets of the universe, we are reminded that we have only begun to scratch the surface of what space has in store. Whether Pluto and Neptune will continue to orbit safely or one day experience a massive collision remains an open question, one that only time and further discoveries will answer. As we move forward in our understanding of the universe, the story of Pluto's orbit serves as a symbol of the mysteries that continue to intrigue and excite scientists. The potential for an impact or close encounter between Pluto and Neptune, though unlikely in the near future, is a reminder of how much we still have to learn about the vastness of space. These celestial events, no matter how improbable they may seem, invite us to keep questioning the workings of the universe and the fundamental forces at play in the ever-expanding field of astronomy. There is always more to discover. As we delve deeper into space exploration, the tools and techniques used to study distant worlds like Pluto are constantly improving. Advanced telescopes, space missions, and more sophisticated virtual simulations allow scientists to track these celestial bodies with unprecedented accuracy. These innovations provide new insights into the mechanics of planetary motion, gravitational interactions, and the long-term stability of our solar system. One of the most exciting developments in the study of Pluto and its orbit is the continued advancement of observational technologies. New space missions are constantly being launched with the goal of exploring distant objects in the solar system. These missions, such as the New Horizons probe, have provided valuable data on Pluto and other objects in the Kuiper Belt, offering a closer look at the characteristics of these distant worlds. With each new discovery, our understanding of these far-off bodies becomes clearer, and we gain insight into the processes that govern their evolution. The fact that Pluto remains an object of interest and study, even after its reclassification as a dwarf planet, speaks to the ongoing fascination with this distant world. Pluto may no longer hold the title of a planet in the eyes of the scientific community, but it still occupies a significant place in the public imagination. Its reclassification has sparked debates about the definition of a planet, the complexities of our solar system, and the ways in which our understanding of space is constantly evolving. This ongoing study of Pluto's path reminds us of the fluid nature of scientific knowledge. What we accept today may change tomorrow as new data emerges and new ideas are proposed. The potential for a future collision between Pluto and Neptune is a possibility that cannot be entirely dismissed, but it also reflects the broader theme of unpredictability in space. The very nature of the universe is such that we can predict with a certain degree of confidence, yet even the most carefully crafted models can be overturned by new findings. The pursuit of knowledge in astronomy is driven by the desire to comprehend the fundamental workings of the cosmos. By studying Pluto and its relationship with Neptune, scientists are not just examining the specific dynamics of these two celestial bodies but also gaining a deeper understanding of how gravitational forces shape the movement of all objects in space. The insights gathered from these studies have far-reaching implications, not just for our solar system but for the broader understanding. The study of Pluto's orbit also highlights the importance of collaboration within the scientific community. Astrophysicists, astronomers, physicists, and mathematicians all contribute their expertise to the study of Pluto's movements, each offering a unique perspective on the issue. This collaboration has led to the development of more refined models of planetary motion and a better understanding of the delicate balance that keeps the solar system in harmony. Although a potential collision between Pluto and Neptune may seem like a distant possibility, it serves as an important reminder of the ongoing challenges we face in predicting the behavior of objects in the universe. The chaotic nature of celestial orbits means that anything can happen, and our understanding of the cosmos will continue to evolve as we gather more data.